So far we have seen a fully connected neural network with a representation of linear algebra. If we can consider the first layer, any one of the neuron, like for example one neuron, the linear algebra equation of the transfer function would be represented as, for example, a w1. If we can represent it, the arcs of w1, w2, w3, w4. So with the help of a associated with connectivity of 1, 2, 3, 4 will be denoted as w1, w2, w3, w4. These are the associated weights and being denoted with the weights of the connections, and from A to the neural nodes of 1, 2, 3, 4, and from B it is being called as the connection of 1, 2, 3, 4 is being considered as W5, W6, W7, W8. For C the connections would be from 9, W10, W11 and W12. So there are three inputs in the input layers ABC. We are denoted as ABC, and for the first layer the neurons will be considered as 1, 2, 3, 4, and for that it is being connected with ABC and the other layers as well. So the connections of ABC inputs with the first layer neurons of 1, 2, 3 is being associated with 12 weights, different kind of 12 weights, and they are being shown in the picture as well. So for that, if we consider only the first neuron, so the equation of the first neuron would be becoming the transfer function equation. If we equation of the incoming input of 1, we can say that AW1 plus BW5 plus CW9 will be the first incoming input equation of 1. So what about the 2? It will be AW2 plus BW6 plus CW10. What about the incoming input of 3? AW, that is called AW, incoming of 3 is AW3 plus BW7 plus CW11, and the last but not the least, the last one, the AW4 BW8 plus CW12. So these are the equations of transfer function that is being computed in a linear algebra manner. So if the neurons are being very less like this way, it can be represented with the help of linear algebra, linear programming style in transfer functions. But when the neurons are getting a little bit of larger, then these equations cannot help or cannot be proceed with this kind of simple manner. So for that we need as help of matrix. So we need matrix representation of these transfer functions, and the computations being computed and passes through the computations to the next layers as well. So how can we map this graph thing into a matrix? So we all are acquainted with weighted matrix. So weight matrix of a graph. So we will just reuse this weight matrix of the graph for this purpose. So let's consider the weight matrix of the current graph. So we can rewrite it: W1, W2, W3, W4, W5, W6, W7, W8, W9, 10, 11, 12. This can be considered as a weighted matrix, a weight matrix graph, where A, B, C is the inputs and 1, 2, 3, 4 is the next layer neurons. So this matrix is a matrix of 3 by 4 matrix. Okay, so for example, when we consider the second layer, So the second layer output neurons will have 4 neurons. So the input matrix can be considered as an A, B, C matrix, which can be considered as column matrix as well. So the column matrix is 3:1, and if we consider some matrix that will multiply with A, B, C, and it will produce the outputs of the first layer neuron. That means it will produce a matrix. Let's say Z1, Z2, Z3, Z4. You can denote it at Z1, Z2, Z3. This is Z4. So this is a matrix of 4 into 1, and this is a matrix of 3 into 1. So to be resultant of 4 into 1, you need to multiply the 3 into 1 matrix with some value that is helpful. That means it must ensure 3 into and the output of 4. If it is considered at m into n matrix, then the multiplication need to be done as r into n and n into r. So from there it is generating actually m into n matrix. So for that we need a 4 into 3 matrix. So in the context of weight matrix, it is a 3 into 4 matrix, and we need a 4 into 3 matrix. So a simple translation of this matrix, like this matrix, the simple transformation will reproduce the transpose matrix like A, B. The transpose matrix will be turned into 1, 2, 3, 4, A, B, C. So W1, W2, W3, W4. The rows will turn into columns, columns will turn into rows. So W5, 6, 7, 8, 9, 10, 11, 12. So it will be helping them W1, W5, W6, so W9, W2, W3, W4, and this will generate a 4 into 3 matrix. This is a 4 matrix and the row columns are 3. So W7, W6, W7, W8, W10, 11, and 12. And after multiplying it, we can say the AW1 plus BW5 plus CW9. And for here, we can also say AW4 to AW3, AW4 plus BW6 plus CW10 plus BW7 plus CW11 plus BW8 plus CW12. So this is how the equations can be reassembled with the help of matrix. So for that we can have a value of Z1 which can be reused in the second layer of the multiplication Z4. It is a 4 into 1 matrix, the outputs of the second layer, and in the picture we have 1, 2, 3, 4, and there you can say if we consider it as a 1, 2, 3 layer at well, so it's a fully connected neural network. So we need to multiply it with some matrix that will produce a 3 into 1 matrix. That means it will produce a P1, P2 and P3. So P1, P2, P3 can be represented as, so the matrix size will be reconsidered as a 4 into 3 matrix, right? So 4 into 3 matrix, it will be considered as 4 into 3 matrix if we connected Z1 and P2s are directly. So the matrix will be represented in a different manner. So because it's a second layer matrix, if we represent it as with the help of the weights, the current weights, considering 1, 2, 3 matrix, So if we consider it 1 2 3 matrix, then how we can consider it? We can rewrite the weights like 3 rows and 4 columns. So 4 columns for 4 Z1s and 3 rows for P1, P2 and P3. So you can rewrite it as P1, P2, P3, Z1, Z2, Z3, Z4, and also W1, W2, W3, W4, W5, W6, W7, W8, W9, W10, W11 and W12. This can be rewritten as this way, but the previous layer W and these W's might get a little bit confused. That's why we have rewritten as the square format, where the square, it is not actually called a square format. It's actually a format that is the representation of the weights in that current layer. So if we can say, it could be rewritten as layer and it could be rewritten as from to. So the W's can be represented as in the form of W layer and from to. So that's how the matrix operation is being performed in the neural network operation, and it can be helpful to compute the layer by layer computation with the help of 2 layers, and it can propagate the results in the next forwarding layers as well. So that's why matrix multiplications are very helpful in the context of this concept. So this is being done in the first layer, which is considered as first hidden layer. This is done in the second hidden layer, and the output of P1, P2, P3 will be moved on to the next outcome, P1, P2, P3, that will be multiplied with some multiplications and will generate the last outcome of the output layer of O1 and O2. Right? So O1 and O2 is a 2 into 1 matrix, 3 into 1 matrix, so we need a 2 into 3 matrices as well, and for that we need O1, O2, and for that P1, P2, P3, and the matrix multiplication would be W1, W2, W3, W4, W5, W6, and it could be rewritten as 3. That does not mean it's a cube, it means the connectivity of the third layer connection. So the first layer connection, the second layer connection, and this is the, if you can consider it, third layer or output layer for this neural network as well. So this is the how the multiplication will be done, and from ABC it will be moved on to O1, O2 and the output layer. So from the inputs it will generate the outputs in the manner of this function. So after computing each layer, the Z1 must be passed to a function. This is called the activation function. So it can be rewritten as that the matrix of function of Z1, function of Z2 and function of Z3. So each value will be applied with the help of activation functions as well. So this is the part of how we can represent our normal multilayer perceptron neurons into a matrix, and how we can consider them in the activation functions as well. So thank you very much for your time, and I hope that you all enjoyed the journey of the matrix operations being performed in the neural network as well. Thank you very much.